is momentum? Have you reflect about it, you know? One thing is to read a definition, the other thing is to think about what it really means, you know? So when we talk about momentum, it's some sort of a measure, right? A measure that involves the mass and the velocity. You see, the formula for momentum is m times v. So it is a measure of
Just a moment.
mass in motion. It's not just mass, right? Because if the mass is not moving, is there momentum there? No, right? So it's a combination of mass and motion. So it's also related to a difficulty to change. When we have two carts here, one has an extra weight and the other one does not have. Without the weight, let's do it without the weight first. This one is at rest and the other one is going to be moving. So there was an easy transition there, right? It transferred all the movement to the other car. But when we have different mass, because they have equal mass, now when we have a different mass, things might work a little differently, right? And we experience that when we have this car going, and you see that this is moving at a lower speed, and this is going back. The other thing we discussed was about impulse, right? What is impulse? When I have a cart here and then I do a little impulse here on the car starts moving, right? But there was a very short time. So impulse is related to a force and a time, okay? And when we did the experiment with the balls, with this one and this one, right? What is the difference when I let it go? You guys remember, right? This one keeps bouncing back and forth, and this one just comes and changes. The change in momentum is drastic on this one, while this one is slower, right? So, but then the question was, if I let both of them go from the same height, what is the change in momentum? We figured that the change in momentum is the same on both of them. But what is really different between this one and this one? The change in momentum is equal to the impulse. But the impulse is the product of force and time. So what is really happening here that I want you guys to understand is that on this one here that is bouncing, it's taking longer time. So we have, if this product is constant, and this is taking longer time, that what you're playing with these two is that the force is going to be less in one case, and the force is going to be higher in the other case, right? So when you think about a crash of a car, you know, if that impact is really, you know, if you don't have a way to slow down, you're going to have a larger force on you. That's what it plays in terms of safety of cars. The design of the car needs to be such to slow down this, increase the bouncing, right? So you have less force. Now, the other thing we also discussed is about kinetic energy. So what is kinetic energy? Kinetic comes from motion, so it's the energy related to motion. So this cart, when I let this cart go, it has mass, it has a velocity, and it has kinetic energy. What is the formula for kinetic energy? Is half the mass, the velocity squared, okay? And then we also talk about inelastic collision. That is a situation where momentum is conserved, but kinetic energy is not. And then we talk also about elastic collision, where both the momentum and kinetic energy are conserved. So what is the difference between elastic and inelastic? In terms of the experiment, is that this would be an elastic collision, and the inelastic, let's see if I can do that here now. The inelastic would be something like this, that they both go together now, okay? So we're going to explore today a little more about these two situations here, how to identify the inelastic and elastic collision, okay? So let's assume that before the collision, we have a body here that has 8 kilograms going at 6 meters per second that way, and we have another one here that is 4 kilograms going at 9 this way, right? 9 meters per second. So when we do the calculation here of momentum and kinetic energy, we find that before the collision, our momentum is 12 kilograms times meters per second. How do we calculate that? We just add the momentum of mass 1, and plus the momentum of mass 2. That is the mass times velocity, plus the mass of the second times the velocity. Now, remember, this one here is going the opposite direction. 9 meters per second is going in the opposite direction, so it's going to have a negative sign here. Okay? So it's kind of taking away the momentum of this one. Okay? Now, what happens after that is what we're going to analyze. Different situations might happen. Situation that is inelastic and situation that is elastic. Okay? Now, when we do the calculation for the kinetic energy, now remember the velocity is square, so the negative sign, it doesn't matter anymore. So we're going to have a value of 306 joules. Okay? Is that exciting? So now the excitement comes now, because we're going to study different situations, okay? So the first situation, see if I get this in here. The first situation, so I'm going to put this in blue so you see the difference. So here now is after. So now here we have so what happened is the little body here now has merged into the other one, just like we had here, right? The inelastic situation. It's like I have one body come this way, and now they go together, right? They kind of press into each other and stick together. It could be like this too, you see? Let's see. what this situation is. So now they stuck together and they are moving in one direction with a speed of 1 meter per second, okay? So what we need to do, we need to do the study of the momentum after, right? So the momentum after is going to be V line M1 plus M2, right? The mass is still the same, the mass of, there was no loss in mass, right? It's just that they got stuck together. So, and now they have a velocity line, V line, it's, because they together, they moving together, so that's one velocity, okay?
Thank you. Thank you.
So that's the side of the momentum. Let's see the kinetic energy. When we do that calculation, so it's going to be M1 is 8, M2 is 4, that's 12. 12 times 1 is going to be 12 kilograms mass. And we notice that it's the same, right? So that means that momentum is being conserved, okay? Now let's figure out the kinetic energy. So this is going to be 12 again, because it's 8 plus 4 is 12. Divided by 2 is 6, and the velocity is 1. 1 squared is 1, so this is going to be 6 joules. So what happens here? The kinetic energy is not conserved. So this is a situation that we can say is an inelastic.
Professor,
Yes.
why did you put minus 1/2 mass times velocity squared over there as well, on the second board,
Where, here?
over here, originally?
Here?
Yeah,
Because this is the final
yeah,
and initial, the difference between
Oh.
final and initial, right? Right? So if an object, like here for instance, right? In this case, does this object has any kinetic energy now? No, right? So V I, right, initial is 0, so this term goes away. The moment I give an impulse here, now I have a kinetic energy, so, okay? But here, what we're doing, so you might have a problem like that, showing this situation, and then they ask, calculate the momentum, calculate the kinetic energy, and identify if this is an elastic or inelastic, okay, collision. So that would be, you know, a question that has 3 parts of it. Each one has some amount of points. Okay? So let's study now the second situation. So the second situation, we have the 8 kilograms, but this one now is moving that way with the 1 meter per second, and the small one moving that way with 5 meters per second, okay? So again, let's do after the sum of momentum is gonna be M1, V1 line plus M2, V2 line. And the mass is 8 times the velocity is going opposite direction. You have to remember to put the negative sign. -1 plus M2, M2 is 4 times 5. So let's see, so this is gonna be -8, this is gonna be 20. 20 with -8 is 12. So excellent, so this is, again, we proved that the momentum is conserved. So you write down momentum is conserved. Then we're going to do the kinetic energy again. For this case, M1 V line squared plus 1/2 M2 V2 squared. So it's going to be 1/2. M is 8. This is 1. One's -1. Square is 1 plus 2. This is going to be 4. And then 5 squared. When we do this calculation, we're going to find that this is 54 joules. So you find 54 joules. That's the final kinetic energy. This is the initial, right? So it's not the same, so it's not conserved. So what are you going to write? It is inelastic collision, right? Okay. So in my notes, there are other examples that you go through. I'm going to skip some of them. Let's go to another one now. In this one, I have the 8 kilogram here, and this is going back with 4. And then I have here the 4 kilogram, and this is going with 11 meters per second, okay? Again, the sum of, yes?
Before you move on, the last question, instead of, you put +1, it's not supposed to be -1 since the direction is the negative?
Yeah, that's true, yeah, I did that here on the momentum, but here on the kinetic, the velocity is squared,
Oh,
and when we square, the
Right.
negative sign
okay, sorry.
becomes positive. And here, let's do 8 times -4 plus 4 times 11. And when you do that calculation, you're going to find 12. Again, momentum is conserved, so now let's do the kinetic. And this is going to be 8 times 4 squared, 4 times 11 squared. And when we do this calculation, we're going to find 306 joules. That is the same as we had here, okay? So now in this case, what are you going to say about this collision? What kind of collision is this one?
Elastic.
This is elastic, okay? So you write down, this is an elastic collision, all right? Let's go to another one. Try to do it here. 4. And this one, we have 6 second, 8, and here we have 15 meters per second. And when we do the calculation for the momentum, we're gonna get the same, 12, so the momentum is conserved. And when we do the kinetic, so P line is gonna be 12. And when we do the kinetic, we're gonna get a number that is 594. So, what situation is this one? The energy, the final kinetic energy is larger than the initial kinetic energy. So what do you guys think is happening here?
Accelerating maybe? Accelerating maybe?
It's accelerating? Yeah. Maybe, yeah. So, what would you write on your notes? What do you think?
Me personally?
Yes.
It doesn't matter what I think.
No, it doesn't matter, come on, yeah.
One of the objects has to be smaller than the other one, that it gets pushed back like a higher rate.
Well, there were other situations here that this was smaller, right?
Yeah.
So somehow there should be a way to create more kinetic energy, right? Somehow I could think about maybe an explosion, right? Right? If something explodes, start, convert chemical energy into kinetic energy. Could be a spring that is, compressed, and when these two objects collide, this spring release and then increases the kinetic energy. But I would say it's not very, it might not happen, this kind of thing, right? So I would say this is improbable situation, okay? So let's analyze one more, the last one. The last one, we have one object going at 8 meters per second, 8 kilograms, and then the small one, 4 kilograms, and is going at 5 meters per second. Okay? Well, let's do the momentum. So here we have 8 times negative 8 plus 4 times 5. So 8 times negative 8 is 64, negative 64 plus 20, so that gives me a momentum of negative 44. And the initial momentum is 12. So what do you guys think about this one? It's impossible, right? This one is impossible because momentum is not conserved at all, right? Kinetic energy is going to be the same in this situation, but the momentum is not conserved, so you'd have to say this situation that it is impossible. All right? So you have all the scenarios here. You just need to go over and review and try to understand why is inelastic, why is elastic, why is improbable, and why is impossible, okay? In which situation. In summary, momentum has always to be conserved, and if the kinetic energy is conserved or not, if it's less, it's inelastic, if it's the same, it's an elastic collision, and when it comes to higher value of kinetic energy than the initial, there has to be some kind of source of energy, internal source of energy, right? Like an explosion or a spring under pressure that is giving away more kinetic energy, so the value is higher. But in the case that you have a negative, different momentum from the initial, then in that situation, it is impossible. Yes.
For number 4, what kind of collision did you say it was?
It's impossible.
No, that's number 5.
Number 5 is impossible because this is low probability, improbable, right?
I think
Is
you're
that a good
stuck.
word or not?
Oh, for number 4?
For number 4.
Okay.
Wait, I thought for number 4 you said there could be a collision, like, or like a,
Yeah,
Explosion.
in case of an explosion, but if you look at the other examples that we are going through, you know, it's just two balls colliding or two cars colliding in a situation like that. This would be sophisticated experiment, right? To do that. And, so, yeah, that's why I said it's low probability. Yes.
3 is elastic?
This one?
3 is elastic?
3?
Yeah.
Yeah, 3 is elastic because the momentum is conserved and so the kinetic energy.
What would be completely inelastic?
yeah.
Complete, huh?
Completely inelastic.
Complete inelastic is a situation that you have a very small
Very small.
energy. Yeah, this is almost, I could say this one is a complete inelastic. Because this has changed from 300 to almost 0, right? So that is going towards a complete inelastic. And when it comes to something like 54 or higher, I could say partially elastic. But, you know, I don't care about this kind of differentiation. You could just say elastic or inelastic. It's fine. Number 2, yeah, number 2 is inelastic. Why? Why is inelastic?
Because the momentum and the energy are not conserved.
Because momentum is conserved, but kinetic energy is not. Kinetic energy has reduced, lost, you know, don't just memorize or, you know, it's not the same, right? Try to understand why this is happening. Well, if it's less, why you think it is less after the collision?
Momentum wasn't conserved.
Huh?
Momentum wasn't conserved.
Momentum was conserved, we calculated that, momentum is 12, momentum is conserved,
Okay,
but the kinetic energy is not conserved, so what does that mean?
Kinetic energy converts to another heat or light.
Yeah, there were losses, right? There were losses. What kind of losses? You know, could be heat, sound, those are all sources of losses, okay? So, because there are losses, so we call that inelastic. It didn't transfer all kinetic energy to the other one. Right? How's that? Is that okay?
Professor,
Yeah.
before we move to the next thing, could you explain to me like how, like to define whether it's gonna be elastic, inelastic, or impossible to solve or anything?
Okay, so, momentum, you understand momentum is mass times velocity, right?
Mhm.
It is a vector. So because it's a vector, you need to pay attention to the signs. The negative sign here is going to affect the result, right? So you need to pay attention if this one is going that way, this one is going that, would be different if both were going that way, all right? I would add here the momentum. But this is the initial situation, before the collision, right? We calculated the momentum when we got 12. So we calculated the kinetic energy. Kinetic energy is not a vector, it's a scalar, okay? And because of that, you know, this value,
The joules
it doesn't
per
matter
kg.
if this is positive or negative, it's gonna be 306 joules calculated. Now we have here different scenarios.
That's based on the first question, right? All
This
those,
is,
the
this is all
collision,
one problem.
everything,
This is
okay.
all one problem. This is one problem, okay? Now, on the exam, you could have this situation, this is the initial, and this is the final. And you do this analysis, and you calculate, and you come up with your conclusion.
Okay,
So in this situation here, now I have different situations, right? In this situation, these two bodies got stuck together. So you know already this is gonna be an inelastic situation, but you need to prove that, you need to calculate that, okay? So we have here the velocity of 1 meters per second. Now the mass now is together, right? So you add M1 or M2, multiply times that, and you figure that you have the same momentum as before.
mhm,
Momentum is conserved. So that when we do the calculation for the kinetic energy, we find that kinetic energy is less than before. So that means there were losses. And because it's less, this is going to be an inelastic collision.
okay,
Inelastic means that you having losses.
okay.
So the other ones, you do the same calculations and you verify that momentum is conserved on this one. And here again, I have the kinetic energy less than before, right? This is after, it's still less. This one here was much less, right?
Mhm, yeah.
More losses than this one here, okay? Now, when we go to the third example, we check that the momentum is the same and the kinetic energy is the same. So now we know this is a situation where we have the elastic collision, right?
Mhm.
It's the same as this one here, that that's elastic, okay? It transfers completely not only momentum is transferred here, but the kinetic energy is also transferred. Because this one has the same mass as this one. And this one is coming with this velocity v, and this is now, it has stopped, and this is continuing now with the kinetic energy.
Makes sense.
Exactly the same kinetic energy, all right? That's different from having sometimes it works, sometimes it doesn't. It's different than having this situation here. This is coming with the speed, and then now it's much slower, right? So, and then we have the example 4. In this example, when we did the calculation for the momentum, we got the same, was conserved. But then, when we calculated kinetic energy, it was much higher. So energy has been created from somewhere, right?
Mhm.
And we could kind of imagine that maybe there was an explosion or something, but you know, that's probability is low for
So
something
that's
like that to
elastic.
happen for
That's
this
elastic.
kind of experiment, right?
For number 4, would that be elastic since that the kinetic energy is greater than
4?
from where we started? Yeah. Or does it have to be the same to be elastic?
Yeah, number 4, what we would say is that that's not a very probable situation, you know.
So it's only elastic
You
whenever
can
the numbers
speculate,
equal.
there was an explosion
Okay.
or something like that. But you would say this is not very probable, right?
Yeah.
And the last situation where the momentum is different, was not conserved, then for sure in this situation, it's impossible. Is that okay? All right, so let's move on now to the next topic. And let's talk about work and energy, okay? So, so let's say in this situation here, this guy grabbed some weight, right, lifting some weight, and he's holding it, right, like that. Very strong, and I bring this up and I stay like this. Am I doing any work?
Yeah,
Yes?
No, there's no direction.
you have to put some energy into holding up the ball, so I'd say you're doing some work.
That's I don't know.
Is energy, and work? Yeah, I mean, what is the definition of work?
Work times direction.
You're going to work for fucking.
Yeah. It has to have a movement, right? Work has to have a force and also has to have something moving, okay? So if I apply a force and there is no movement, if I come to this wall and I keep pushing, am I doing any work?
A little.
I'm
You're
not.
trying.
Very little? Yeah. You have to do work, you need to move something, right? If this thing is here, it's not moving, and I'm trying to move and not going anywhere, I'm not doing anything. Okay? Has to transfer this energy into something. If I'm just holding there, I'm just wasting my energy there. It's getting tired, right? I'm getting tired, yes. But I'm not doing any work. Work has to have a movement, right? So if I move this ball from here to here, yes, I've done some work, right? Because I can get that back. How can I get that back? I'll just let it go, right? Do this and I get something back in return. When I do this here, I'm not getting anything back, right? Besides hurting my hand, right? So I'm not getting anything back. So work is a stimulus and is the product, the dot product of force times the displacement, right? So if there is no displacement, then there is no work. Is that okay? Work is an activity that involves movement. It has to involve movement. So in this situation here, yes, I'm putting a lot of effort to keep this, holding this thing here. My arm is hurting. I'm getting tired, right? I'm wasting my energy there. I'm not doing any work. Is that okay? Think about, it's an activity that involves movement and getting some return of it. Right? That's why we say, it's more than just, like sitting in a computer, just thinking, right, and exercising your mind, that's not work in physics, okay? It's more than just a physical effort, because this is a physical effort, but it's more than that. It's a mental effort because I have to concentrate to keep holding this, plus physical effort to keep holding this, but this is still not work. I have not produced anything. Okay? So in this case, it's no work. In this case here, there is no work either, right?
No.
So the dot product, if you guys remember, the dot product is the product of the magnitude of the force times the magnitude of the displacement cosine theta, right? So in this case here, I am applying a force, and the force needs to be in the direction of the movement, okay? I'm applying this force here, so I have to calculate the component of my force here. That's why I have the cosine theta here, right? The cosine is to ensure that this force is in the same direction than the displacement. If theta is zero, right? Cosine of 0 is 1, then it's force times distance. Do you understand this formula?
Mm-hmm.
So this is important to think about also, right? It is the component of this force that is going to produce the work. It's not the whole magnitude of the force. If it's not aligned, it's not going to be, so you basically wasting some force here, right? If you put the same force in the same direction, you have more work. You're wasting work when you're doing that. You're pushing your car this way, so you're spending some time, some energy, some force going in the wrong direction. If you do a line horizontally, you use more. Now, let's think about this situation here. Now I'm carrying a bag, I'm carrying this ball like this, right? And then I'm moving in this direction. Am I doing work?
Yeah.
You're the one who's moving, but you're not putting any force neither. There's no displacement on the ball.
Well, I'm putting some force so I can, if we're not putting some force, this thing would just drop, right? So I'm holding this way, but I'm moving in that direction. What do you guys think?
Well, you have a direction and a force, so technically by that, you should be doing work, right?
You have a direction and a force. Yeah, but you need to think about what is the direction of the force and what is the direction of the displacement. And if you look at this, what do you think?
Positive.
What do you think? What is theta here? When I'm moving this way, what is the value of theta?
Cosine is 1.
Huh? The force is going this way, right? And the displacement is going that way. So what is the angle between the force and the displacement?
90 degrees.
Huh? 90. So if cos 90 is here, what is the cosine of 90? 0. Okay? It's 0. So, do you guys remember when we were studying circular motion? On a circular motion, the centripetal force is towards the center, right? Remember that, centripetal force is towards the center. The displacement is perpendicular to the centripetal force. So does the centripetal force produces any work? What is the work of a centripetal force? Those are going to be questions, okay, on the finding.
Maybe gravity?
Huh?
Gravity?
Gravity? No, we talk about two different things here. This is the centripetal force. I'm asking, what is the work done by a centripetal force?
Force times the displacement.
Huh? Force
Times the displacement.
displacement. So the force is going towards the center. The displacement is perpendicular to the force. So what is the value of the work? How much is the work? Can you calculate that? Zero. Right? Why? Because this angle here is 90. You plug in here, cosine of 90 is 0, so there's no work. Centripetal force produces no work. Carrying a bag like this produces no work. Okay? All right. So now let's talk about power. Okay? Now, I have this thing here. Right? And I come from the floor and I bring it up like this. Right? Am I doing work? Pick up here from the ground and I bring it up. Am I doing work? Yes, right? Because now I'm moving this up, right? So the force and displacement goes this way. So, but there is a difference between Eugene's like this, right? And my cousin that goes very slowly, right? So, what's happening there? Is the work the same on both situations or different? Huh? If I pick up this fast and go up, or I pick up this slower and go up like this, is the work has changed or is it the same?
I think they'd be different potentially. If one's going faster, you're probably pushing with maybe greater force. You're stronger.
Well, let's talk about potential energy. Is the potential energy the same? If I bring this
No.
up from the ground to this height. If I go up faster, if I go slower, is the potential energy the same?
No.
Or different? Huh?
Different.
It's different, the potential energy? What is potential energy? Potential energy is related to the height, right? The higher, more potential it has, right? If I let a ball go from this height, what kind of speed is gonna be there? Arrive on the ground. Is that gonna be less or higher than if I put this even higher, right? The highest I let it go, the highest is gonna be the speed on the ground. You guys agree with me with that? So it has transferred more energy into kinetic energy because of the height, right? So the kinetic energy on the ground, the speed that it arrives on the ground is going to depend on the height. If I send it from here, or if I send it from here, you even hear even the noise, right, was louder, right? Because that's, you know, because this here is an inelastic collision, right? If I let it go from here, did you see the difference? If if I let it go from here, small noise from here. So I think that relates to the fact that it is higher, it has more energy, more potential energy. Okay? And more potential to convert this, to produce energy. More potential to produce energy, right? So if I'm doing this here now at a slower pace, or if I'm doing this at a faster pace, and if I bring this to the same height, if I do this slowly, or if I just go like that, the height is the same. When I let it go, it's going to convert the same amount of kinetic energy going to the ground. So one thing